So, good afternoon to all. I'm Serge from ST Microelectronics. I'm very honored and delighted to stand in front of you this afternoon to share how artificial intelligence is boosting our R&D. And through this presentation, we'll explore the way of transformative role of the artificial intelligence in semiconductor design, in edge computing, and also in innovative sustainability. So today, artificial intelligence is a part of our life already today. And when you look to all the sectors which are listed here, you can take examples. In the area of automotive, you go just in the streets of San Francisco and you will see the Waymo vehicles, which are autonomous thanks to AI. Again, about vehicles, if you go to space exploration, the rovers of the NASA on Mars are driven by artificial intelligence to explore, to take samples, and so on. If you go to gaming, our children are playing, obviously, against or with other real players, but also against non-player characters, which are generated by AI. So there are many areas where we can find how AI is contributing to this area. And it's enabled by our industry, in fact, by our R&D. And the key question maybe is where it is starting from. So it's starting from our human intelligence. It's starting from the way we are creating technologies and realizing products which are mimicking our natural body capabilities. So it means sensing our surrounding environment. It means acting on our environment and our world. It's also meaning to be connected with others, to grab information, to memorize it, to process it. And we are creating those chips. So it's why we are talking about sensors, we are talking about actuators, we are talking about connectivity, and at the end, processing unit, either MCU or MPU. And this is bringing the information from the physical world to the digital world. It could be locally or it could be in data centers. But what's going on in addition is this link, this bridge is augmented by artificial intelligence. So the data which are created are helping to learning artificial intelligence algorithms, mostly in the cloud. And when the learning is done, then these algorithms are able to run either in the center, data centers, or at the edge, locally, where the data are created. So let's imagine how much we are, let's say, building steps of computational capabilities along this chain. And this is spread along a pyramid, which is called the computing pyramid. When we look to the data centers, the numbers in thousands. When we go to the next stage, which are the edge gateways, the numbers in millions. And when we are going very close to the physical world, to the teeny edge devices, here they are numbering in billions. And this is very much this area where you can find AI, which is processing the data where they are just created. So let's maybe have a look at two examples. The first one is about microelectromechanical systems, MEMS. And you know, there are two types of MEMS, the sensors and the actuators. If you look to the sensors, they have the capability to measure physical quantities, like acceleration, like pressure, temperature, magnetic field. And we are creating chips which are able, obviously, to measure these quantities, like accelerometers, gyroscope, pressure sensors, and so on. Here, you have an example of a smart 6-axis inertial measurement unit, which is embedding a digital signal core. And this digital signal core is running a machine learning algorithm, which is able to manage the wake-up of the system in an intelligent manner when there is an event, but in the same time, to preserve the power, considering it's eligible for wearables, where it's important to manage the battery and the battery lifetime. And you can find more generally two types of sensors, either embedding this type of machine learning solution, or more complex with intelligent sensor processing unit, which are able to run more complex algorithm, artificial intelligence algorithm. And here you can appreciate an heterogeneous integration solution when you have multiple silicon chips, which are in the same package, connected each together to provide this solution, thinking about the capacity that we have to provide to our customers. The second example, it's about microcontrollers, MCUs, microcontrollers units. We are finding microcontrollers everywhere. You are finding it at home, in home appliances like air conditioning, in your coffee machine, in the dish machine, the wash machine, everywhere, even in the industrial part. When you are looking to fabs, you can find microcontrollers in the robots in multiple areas of the fab. So what we are, let's say, seeing is increasing adoption of artificial intelligence solutions embedded into microcontrollers, from software to hardware. And this trend is having a very high level of growth. These are the forecasts which are given here. And moreover, we see a good traction in terms of developers. We are adopting those microcontrollers to develop their own app solution on the final systems. We are even partnering with big guys. You can read their name, NVIDIA on Amazon Web Services, for this type of activities. And why? Because in the future, the workloads for the microcontroller will increase further. And to answer to this increasing aspect of the workloads, we have to develop neural processor unit. We have to have a roadmap, which is improving the number of operations per second, typically tera operations per second, which is a key metrics about this. And we'll see later also the power efficiency. And today, we are offering a first microcontroller with an NPU, which is 600 times better than the highest performing MCU we are offering earlier. And this has a very good traction by the market because it's one of the fastest products where we are getting $100 million of revenue. So here we have two examples. And more generally, Edge AI is bringing a lot of benefits. We are coming back on the data creation. And what do we do with the data? Are we keeping the data locally, or are we bringing everything, every raw data, to the cloud? And in fact, the idea is to bring only pertinent data to the cloud, which means we are preventing to transfer and to consume energy for transmitting data without any meaning. We have to remember, maybe you're having this in top of your mind, when you look to the overall data centers, their power consumption on the forecast by 2030, overall data centers will use the power which is generated by Japan in 1 year. And Japan is a country of 123 million of people, and in the range of 1 terawatt per year. So it's very impressive. So whatever we can do, 1,000 terawatt in a year. So what we can do, obviously, with Edge AI, we are preventing, let's say, this type of explosion in terms of power consumption. There is another important aspect, which is the privacy. Since data are stored locally, and which could be confidential, and which could be also protected by laws, because there are some regulations in this area, the data are not transferred to the cloud, are not going through internet, it's stored locally. The third aspect also is obviously when you are in an area which is not connected to the network, and you have to have a solution in real time to handle, either on a car, when you have a microcontroller on an airbag, or on any other applications where there is a need to have a decision without the cloud. And this is why it's important to have also this capability of computing at the edge. And when we look more forward, the way to improve the computational efficiency at the edge, we are moving towards the analysis of the architecture which is underlying the computation. And for 80 years, everything almost is relying on the von Neumann architecture, which is let's say, linked to a Hungarian-American mathematician and physicist who created this architecture. So on one side, you have the unit, which is taking care of arithmetics and logics, and on the other side, you have the memory. And all is about data transferring from the memory to the unit. And this, as you know, is consuming a lot of power. And what is getting more traction, what is raising is the concept of in-memory computing, which is called sometimes computed in memory. So you can find the two acronyms, IMC and CIM. And here you are leveraging by implementing some basic mathematics rules, some basic mathematical functions in the memory. So it means either summation or multiplication. And it's possible because we are remembering especially the Kirchhoff's law, and it's possible. So it means you are doing a first stack of elementary, let's say, functions which are underpinning the AI algorithms. You are preventing too much traffic towards the unit, and you have at the end a result which is lower power, more efficient, and in the same time you are improving the compute density per area. And this is what is feeding our vision. And to appreciate the way we move from one step to another one, we have to look to the axis. So the horizontal axis is about compute density. So it means tera operations per second per square millimeter. You can also appreciate at cost level, because you know the cost of the surface of silicon, so you can also consider it as a cost indicator. But anyway, it's a compute density. On the vertical axis, which is critical especially for battery-powered applications, you are looking to the power efficiency. So tera operations per second and per watt. And our vision is to move progressively from acceleration, neural acceleration, towards digital in-memory computing, towards hybrid memory computing, which is embedding both analog and digital in-memory computing. And we are envisioning, obviously, this progress thanks to the system technology optimization, because when you look to the final system and you are capable on the other side to optimize the technology, the memory, the non-volatile memory, then you can play on the design. You have all the full chain to be able to have a fully optimized system. And this trend is also, this approach is also calling for a set of questions. Because when you are designing a neural processing unit, you have to think about the number of processing elements you want. What will be the size of those processing elements? How much you want to parallelize them? Will it be in integer? Will it be in floating points? And then when you have those considerations, you have to look how you are accurate, how your system will be accurate. Will it be enough accurate for the needs of your system? Will you have enough throughput and at least real-time capability with the system? So it means throughput, latency, the other side, and as a consequence, you will have to check energy and power. So will it be enough energy efficient? Which kind of power you will have to sustain for the system? And for sure, you have to consider the mission profile of your system. Will it be for 10 years? Will it be for 5 years? What will be the range of temperature and so on? So you have all those set of questions. And finally, yes, you have to also propose this product to your customers. You have to consider the cost. And the cost is pretty much driven by the way we are combining the compute density, the number of masks of your technology, and obviously the wafer itself. So this is a trend which is very much recognized, and when we look to ISSCC conferences on the trend in terms of publications regarding IMC, either at micro level or at micro level or macro level, we see this kind of trend, this kind of increasing publications level, coming either from universities, from research technological organizations, but also from foundries and from IDMs. So this is very much boiling, this is very much rising, so we are also very excited to see in that conference this growing, let's say, visibility on IMC. So there is a natural transition when we talk about AI with chiplet, because chiplet is a design approach. Why? Because you are starting from your experience in a monolithic design, your system on chip, and you have to appreciate and to find a way to de-integrate all parts, all modules, all functions in a smart manner. For sure it will provide scalability, because since you are able to decouple by modules, some modules will be able to evolve independently of others. It's modular, by construction, you are having all the possibilities, and you can select the best technology platform for each of the modules. You are not obliged to find a one-fit-all technology answering to all the needs. And it's also something which is calling you for cost. And what is the cost? We are moving from the one big chip, system chip, to multiple chips. So as you know, lower size, higher yield, and somewhere you are gaining. And for this, we have launched an initiative which is obviously addressing this challenge, moving forward from system on chip integrated monolithic to chiplet approach. We are leveraging on one technology we are mastering in terms of assembly. It's called panel level packaging, PLP. And what is PLP? Well, in a nutshell, you are realizing, let's say, either RDL, redistribution layers, or direct copper interconnections between chips, obviously neighbors chips, on a panel of 70 centimeters by 70 centimeters. For sure it's different versus unusual circular substrates which are used in packaging. And this is a solution today we are using in mass production in our plant in Malaysia. And today you have some pictures we are sharing with you where you can see the famous panel. It's 70 centimeters by 70 centimeters. We are producing 44 million units per day, and we are the first in the world in this activity. So thanks to this technology, we are complementing our chiplet approach, and we are going to build a pilot line for next year that will go to the next generation of panel-level packaging technology by improving the design rules, as well by increasing the eligibility of the chips that will be embedded on the panel. And in this design space, complementary, we have to think about the way we want to interconnect. We want to interconnect those chiplets. And here you have, obviously, 4 challenges to be captured in terms of bandwidth and latency. So which kind of data rates are you looking for, obviously? It's calling by the system when you are breaking down to the chiplet itself. In terms of power efficiency, because you have to manage the overall power budget. In terms of signal integrity, thinking about all the lanes to interconnect the chiplets. And those lanes will go very fast. And you have a lot of signals. It means there is the high risk to have crosstalk, with the aggressors and the victim. So you need to take care also of the crosstalk. And then the cost. Because when you look to each chiplet has to have an high-speed interface to be connected with the others. So it has a cost in terms of area. So you need to carefully evaluate also what you are bringing in terms of value to your chip. And for appreciating and to have some numbers on top of our mind, here we put two examples. So UCI Express from one side and AIB. And we put the numbers, which are public ones, where you can appreciate, let's say, the speed. It has to be addressed in terms of gigabit per second per lane. We are talking about latency. You have some example. One which is interesting is the number of watt, milliwatt, or microwatt you want to give as a budget to your interface. And it means when you look at the bit level, you have to consider for sure picojoule per bit in order to have at the end, at the global and at the system level, a picture which is still in the budget of power. Regarding signal integrity, you have here an example about crosstalk, the way to appreciate the crosstalk. And last but not least, moving to the cost, thinking about the design overhead to handle those interfaces, you can take some targets in terms of number of kilogates you want to bring to challenge your interface. And obviously, you want to reuse as much as you can the PHY architecture. And this journey in the design space is taking another dimension when we go to 3D. We're talking about panel-level packaging, which is a 2D approach. And here we are moving to 3D. So it means wafer to wafer, die to wafer, or wafer to wafer to wafer. And it means, again, same challenge, how do you partition your system? How do you partition your historical monolithic chip into multiple layers and chiplets? How do you appreciate the way clock and power will be delivered into the complex 3D architecture? How you are taking care of thermal dissipation? Because obviously when they are getting closer, when they are all together, how do you evacuate? But moreover, how each chip is affecting the behavior of the neighbor or of the neighbor above and the neighbor under. And you have to check also how you can handle verification of your global system at the end. Last but not least, maybe some chiplets are discussing only with the other chiplets. So how you can inject test patterns in order to be sure you are able to get rid of any issue that could be, let's say, part of the architecture. So it calls for a more robust automated tool. And I'm glad, and you are glad, I suppose also, to have seen in DAC conference a lot of evolution and revolution in AI adoption for EDA tools. And moving beyond, so where could be the benefits of AI? And this is our vision. On the horizontal axis, we start with, let's say, optimization. We start with optimization thanks to artificial intelligence, machine learning. We start to have GenAI with chatbots, at least helping experts to go faster by taking care of, let's say, usual routines, but also helping to onboard new talent in your organization. And then you are moving towards design copilot, involving orchestrators and agentic AIs. On the vertical axis, what could be the benefit when you look to the design flow? You are looking obviously about quality. You want to make sure that what you are designing will be functional and will be reliable. So quality of results, quality of flow. You have to manage also time to market, so the turnaround time. Then you are looking to more and more secure, let's say, earlier in the stage of development with a shift-left approach, not chiplet. And then looking to seamless integration for 3D onto the cloud. Because more and more, the computational power you need to realize the chip is calling for CPUs, GPUs, so you are moving naturally to cloud. Last but not least, there is all the challenge about analog synthesis we are expecting to see in the coming 3 to 5 years. Now we have to remember, when we talk about artificial intelligence, we need to do learning of the system. So what will be the data you will be using for learning the system? Will it be the data coming from all EDA? Will it be your own data? Will you be mixing this? Will you be taking data coming from other sources? What will be the level of trust you will have in those data, and how you will prevent IP contamination when you are realizing your product? So this is also a set of questions which is part of our vision, where we need to answer to. And to illustrate the transition towards R&D and our day-to-day R&D activities, sometimes there is no tool which are existing. It happens. Yes, it happens. There are some tools which are not existing. So we are trying to see how we can explore and boost our R&D activities and development thanks to artificial intelligence. And the idea is to gather from one side the experts. We are having 10, 15, 20, 25 years of experience. We are very well mastering their field of activity, but they are far less knowledgeable in artificial intelligence about concept, about the way to handle it. On the other side, we are bringing young talents as PhD or as interns to work together on a concrete case, not a theoretical one, but a concrete case which will make people converging and discussing together. You have a kind of reverse mentoring because the young talents are teaching a bit about artificial intelligence to experts. And this activity, we launch it by following what is so-called design thinking approach in 3 steps with sensing, sizing, and transforming. And you can appreciate the various cycle time of each phase. When we talk about sensing, it's about the project you want to target, you want to handle. And to illustrate this journey, which is now lasting for 5 years, you see the number of projects we have been running and over those year by year. From 2 at the origin, just to discover, now we are running 40+ projects this year, which are aiming to address various types of topics. It's about design enablement, it's about optical design, it's about process recipe, because the job of R&D is to develop also process recipe into the fab. It's about reliability and also TCAD and some others. And among our projects we are running right now, 40% are in the phase of transformation. So it means are going to be deployed in our, and to be spread in our way of working. And when we look to this journey, which is good, we have been able to embark a lot of people, hundreds of people. So you see the culture is changing. It's no more just a tool. We are talking about the culture and the way of working, and the way of adopting artificial intelligence, not by plugging it by top down. And I would like to share 2 examples with you. The first one is about SPICE. So SPICE, you know, is very important because the model, the way we are representing the electrical behaviors of our devices are key to get at the end a design which is functional, which is robust, which is reliable when it will be on silicon. And more, the way to build these models, to extract, it's called model extraction, to extract the model from the silicon is becoming complex because you have a lot of interdependencies between the devices. And as you maybe are remembering Frank Herbert's series of book Dune, whoever controls the SPICE controls the entire universe. So it's why it's so important to address this challenge. So how do we handle this point? We are using a 3-steps approach. The first one is to build a space of model, let's say a training database. So we are taking existing model cards, which are typically representing V, I versus V for each devices, geometry, each temperature, and so on. We are doing LDO simulation, and after that, we are expanding the training database by a genetic algorithm to have enough, let's say, to be in the range of 0.3 millions of reference cards. After we have built this database, we are feeding the artificial neural network, which is running also, let's say, a complex log loss equation, log loss function to converge and to learn fast. And when we have learned the system, then easy, between quotes, you take the data coming from silicon, you run through the deep neural network model algorithm, and then you get the model card. Bon, the point is obviously to check whether these model cards are real or are hallucinated. And this is what we did. So we selected multiple technologies. Here you have the examples of 3 technologies, one in 200 millimeter, 2 in a 12-inch, digital, or one technology which is dealing with embedded non-volatile memories. And we are looking to some VTs to see how we were able to match what was already extracted, and we get pretty good results. And what was also very interesting was to look to the time we were gaining in terms of let's say, expertise of the people. And we transform some tedious activities of extraction of spice model of weeks in few seconds. So it means what is remaining is addressed by experts to handle the most complex case. I will take now another example, completely different. Among the technologies we are handling technologies not only on silicon, but also on glass. We are in the space of diffractive optical element. And these diffractive optical elements are relying on specific structures which are put on a glass wafer. We are calling it metamaterials. Because those materials, those structures, you will not find it in the nature, so it's why it's called metamaterials. And when you put these metamaterials on the glass wafer, you want to know whether you will get the figure, the shape, or the image you are targeting to have. So here you have an example. Let's consider the metamaterials are a type of pillars we are putting on a glass wafer. We want to make sure that the pillar structure will generate the ST logo. So you need to run a simulation. And there are some tools which are existing, commercial tools. And when we look to the size and number of pillars we want to address, we see an explosion in terms of running time. And even when we reach larger matrix, this is no more working. So again, we develop artificial intelligence solution in this area that we train. You will see after 2 examples, which has been able to let's say, answer to our challenge. And we went from, if you take the 128 by 128 pillars, matrix of pillars, we went from 1 day to 150 milliseconds of simulation. So what does it mean? It means you can run faster iterations. Instead of waiting 1 day to understand whether you are going into the right direction or not, you can run in 1 day multiple of iterations to see whether you are going into the right direction. The other aspect is you have a pattern and you want to do the reverse design. You want to go back to what will be the pillar structures, the metamaterial pattern you want to have on the glass wafer. And remember, it's diffractive. We are talking about Fresnel optics. It's diffractive, so it's why it's take also. We have to look to the commercial solutions, and here there is no commercial solution. So we have been able to develop a solution by ourselves, and it took a bit time, but we have been able to have such a solution. You see again, 25 seconds for a set of pillars. When we go higher in terms of size, it's taking a bit more time, 4 hours, to explore and to find the right, one of the right most eligible pattern of metamaterials. And right now we are taking the challenge of larger matrix of pillars. And to illustrate, here you have the results of our approach that also has been published, considering the way we are simulating and the way we are finding the reverse design. which is, by the way, interesting to see, because it's not intuitive. If you see to the pattern, it's not intuitive. You have a lot of spikes, so it means a lot of pillars to handle on the glass wafer in order to realize the design. And what we have seen also in terms of benefit, which was not expected, it's kind of serendipity. We discovered something which was not expected, is when we're looking to the efficiency of our solution, not only in terms of timing, not only in terms of getting the results. It's also a matter of looking to which kind of energy we have to bring to make our solution working. So we are obviously looking to ChatGPT, which is calling for a lot of energy for training, but also for inference. ChatGPT doesn't answer to all our business cases, let's say. But when we look to the AI solutions we tailored, and we tailored for those applications, you can see the benefit in terms of power. And we have seen, especially on one case, a benefit which was almost 100,000 better for per technology in milliwatt hour versus what it was done without artificial intelligence. So we are gaining in time, yes. We are gaining also in, let's say, expertise in the organization, because we are mixing young people and expert people, young people coming from universities and let's say on the engineering schools, and they are talking about Python. They are talking also about PyTorch, which is a library associated to Python. I'm still remembering when I was starting many years ago, we are talking about Turbo Pascal, Fortran. So the world has changed, and our experts are more thinking about this type of languages sometimes than the one which is coming right now. So it's good to have those people together. So this is opening a path for sustainability. And sustainability is important for our as citizens. It's important for us. It's important also for our company, and it's in our model. It's in our culture for many years, for 30 years in fact, because it has been initiated by our first CEO 30 years ago. You have a full list of examples here. Maybe I will pick up a few of them. I will underline the Sustainable Technology Program we started 14 years ago, and I will illustrate it, the link of Sustainable Technology Program, because we are developing the technologies, we are developing the products. So the way we are developing the technologies are generating what we are calling responsible products. We have this commitment. You will not find many companies in semiconductor which are committing in 2027 being carbon neutral. And obviously, we are following all the progress every year. So how do we approach responsible products? And but it's quite simple. You look to the product life cycle of a product. You can represent it in 5 stages. The first one is about raw materials. So it means you need to select and to source ethical materials, which are not coming from a conflict area. You need to make sure also they have to be as much as possible compliant with all, let's say, environmental rules. The second step is to develop the product. At the same time, we are also developing the technology. And we'll see, by the way, the eco-design approach in the product development. The third step is about manufacturing. So it means you are taking care of realizing the product while minimizing the ecological footprint. And in the same time, when you are in R&D, you are taking care of the process recipe development. You want to minimize the number of iterations until you are getting the right recipe. It could be in etch, it could be in epitaxy. And here again, we are addressing this thanks to artificial intelligence solutions. The fourth stage is about usage. So which kind of usage will have our customers of our chips? And if we can provide a chip which is providing better performance in sense, better power efficiency, we are contributing to their low power solution. We are contributing to make their own ecological footprint becoming lower. And then, end of the life, we have to say, okay, when the product is no more working, how do you recycle it? How you will take care of? And this is part of our, let's say, vision and approach for our products. And if we look to the product itself and the way we are developing responsible product, we are introducing 2 key important steps in the flow. One at the early beginning, which is the eco-design evaluation. And the second step, after the design has been realized, is to have the eco-design consolidation with the associated checklist, fully answered, to make sure we have mastered from A to Z the design of the product. And when we think about responsible product, we have four, in fact, definitions. The first one is whether this product is contributing to reduce power consumption. The second one is about whether this product is enabling to reduce manufacturing footprint. The third step is about whether this product is enabling green technology or ecological technology, for instance, more efficient wind farm, more efficient solar farms. And the fourth one, obviously, we have to think about us as human beings, is to take care of people, so how we are contributing to the welfare, well-being applications. And this is, as a nutshell, this is what I wanted to share with you today. There is one part which is quite clear. AI now is proliferating in every human activity. And I'm pretty sure at the moment we are talking together, we have AI personal assistant in the place. Huh? It could be Alexa, Bixby, Celia, Cortana, or Siri. I'm sure they are with us. Edge AI is as much important as AI data centers because those solutions are processing data where the data are created. There are many spaces for novel chips architecture, as we have seen. On AI, in terms of design activities, but also technology development, is a reality and will go further in our coming days. Last but not least, we have to think about the global climate change. We have to think about sustainability. And again, it's our industry which is at the heart of taking up this change. Thank you very much for your attention. Alors, I think maybe you can ask some question. There is a micro if you want. Yes, you go to the micro if you want to. Yes, please.
Thank you for the nice talk. I'm a researcher. I come from UIUC. I'm asking about a question about AI usage in the IC design. So you are from the industry, but in academia. So if we want to utilize AI, for example, to facilitate some design space exploration for a chip, we don't have such data set, so we have to rely on some very limited design points or even synthetic data. The second thing that if we want to train a model, so we have to use either maybe LLM based or agentic based. So the training or the fine-tuning model may be a problem for academia because we don't have such large data sets to large compute to train. So could you give me some suggestion or advice to about how to enable AI in academia chip prototyping flow or in a limited within a limited resource or the time? Thank you.
Okay. No, it's a good question. So I will answer with one example. When you look to the healthcare industry, today, 25% of the molecules which are introduced on the market are coming from AI. So they have been fully selected, identified, screened, and then tested in laboratories, obviously, but they are coming from AI. And when you consider healthcare, there are a lot of sensitive data. So it means related to your health, my health, the health of everyone. So those data cannot be shared. So they are developing more and more, which is called federated learning. So it means you have a kind of AI system, and you are having then models which are locally handled, where the training is made locally. The raw data on let's say, the private data are protected, but the model have been trained. So you got, let's say, a first level of training, and then you have to aggregate. Then you have to aggregate at the upper level, let's say, all the results coming out of each of individual model. So this type of approach will gain, I think, more and more traction, because when we are alone, we don't have maybe enough data, but when we are together, we can get a lot of more data, but we want to protect our privacy or our IPs and so on. So this is very much a trend which is, I think, today very well represented in the healthcare world, and maybe in the semiconductor industry, it's also a path to consider in the future.